Warm regards everyone. Today's presentation is Geospatial Technology Application for Small Reservoir Design with Environmental Friendly Decision Support. My student Patrick Perkins, with my advice, developed this work, and I'm Sudhanshu Panda presenting this for your benefit. Let's talk about the background of the research project. So we know that large reservoirs construction closer to urban centers or semi-urban centers are considered to be very environmentally unfriendly because it will inundate a large area and the peripheral forest lands and other special use lands. So therefore, for counties, designing and constructing smaller reservoirs is a prudent approach, as it would be part of the surrounding green space development, and it would help in supplying drinking water, serve as a feature for flood and erosion control. Especially, it will serve as a source of entertainment for local population because it is closer to the urban or suburban center. However, the site selection and engineering design of such smaller reservoirs or water harvesting structures are more complicated, and geospatial technology can be the best tool for its implementation. We know that small reservoirs closer to urban or suburban centers would increase the environmental, economical, and social cultural values, as it would counter the significant negative impact from those development, which will degrade the water quality, create soil erosion, and help in biodiversity or natural habitat loss due to land use change and increase in imperviousness. Small reservoirs in urban watersheds would certainly reduce human impacts on watershed health and thus help in creating a sustainable environment. These reservoirs or water harvesting structures not only would act as a flood erosion control, drinking water supply, and recreational features in the urban neighborhood, they would also serve as groundwater recharging structures, which is the biggest need in today's time due to ever decreasing groundwater table in United States and elsewhere. The objectives or the goal of this study was to develop a geospatial technology supported modeling process to design an environmental friendly reservoir in the area of Big Creek sub-watershed along the Big Creek, which is located in the southwestern Forsyth County of Georgia, with the use of USDA Agricultural Research Service curve number method. That algorithm will be using to develop or design this reservoir. And also another objective of us, we made sure that the design would have the minimum impact of the environment surrounding the urban or suburban center. Study area, you can see that it is in Forsyth County, and we have one of the sub-watersheds shown there. The Big Creek is the down one, and also the picture shows the nearest green space or greenway developed in the forest. So we make sure the design we are doing, this greenway is never get inundated. The Big Creek watershed region is prone to flooding during heavy rainfall events and would be better managed through dam control. We know that water harvesting structures or small dams or big dams, they are a biggest feature for flood control. And this particular area many times kind of flooded. This area is comprised of, the study area is comprised of state protected wetlands. So a dam certainly would benefit the area by helping to maintain water levels during drought and protect animal species or aquatic animals and other animals, wild animals living around the urban center. And also local fauna will be certainly kind of benefited because it would reduce the bank and rill erosion. Big Creek, we already told, it is located in southwest Forsyth County, Georgia. The need for a reservoir is due to uncontrolled flooding during storm events and would provide other environmental benefits. The algorithms, the curve number algorithm that we'll be using to develop the geospatial model, initially to calculate the total amount of discharge or runoff coming to the proposed small reservoir area. So the curve number equation is given here. Most of us, we know this equation, and check that the curve number will help to create the maximum potential retention raster, and from the S raster or maximum potential retention raster, we will create the initial obstruction or surface storage raster, that's IA, and the P raster, that's the depth of rainfall raster, will be created using the precipitation value downloaded from USDA NRCS Geospatial Data Gateway, which is created through the PRISM program, PRISM, it's an acronym. And at the end, Q will be, or Q, or the entire runoff amount or the discharge amount from the entire watershed will be, that as a raster format will be created using the equation shown in the middle. And it is in this slide we explained exactly how the Q raster was developed. First, we developed the curve number raster using the table in the right side. So this one, the table was developed by the USDA ARS folks, and it includes the hydrologic group and the land use combination. So unique hydrologic group and land use combination helped us to create the curve number. So hydrologic group was created using the GSorgo data, and land use classification or the classes were developed using National Agricultural Imagery Program data. So we classified that. Again, the reclassify and plus tools of ArcGIS helps us combining both your hydrologic group raster and your land use raster to provide our curve number raster. So curve number raster provided the S raster provided the I raster. I explained earlier from the algorithm. Then P raster, as I told, from the PRISM program data, we created it as a raster format. Then all these P, S, and I raster combined together using that USDA algorithm to calculate the your discharge or runoff raster or Q raster, and we created that in ArcGIS model builder, and the important tool was Raster Calculator to do this map algebra application. Then the next part is important. Once we know the total runoff coming, so we will be understanding how large the reservoir we should design. One of the important feature to take note here, even if we have the known amount of runoff coming, we cannot design completely based on that our reservoir, because we need to take care, make sure that the high value land and some of the environmentally advantageous land uses like say riparian forest and other things, other land covers should not be inundated. So we use 1 meter digital elevation model that was created from the LiDAR data, LiDAR point cloud. We obtained it from the Georgia Mountain Regional Commission. They flew that in 2015. So discharge and runoff raster provided us about the filling time, how long will take. Generally, we would go for 2 years to fill the reservoir, entire volume. Then we use ArcGIS Pro for modeling purpose, and ArcGIS modeling discharge modeling purpose, and ArcGIS ArcScene module was used to develop the 3D representation of the reservoir basin for performing volumetric analysis. ArcScene based reservoir 3D representation model result helped us showing the boundaries of the flooding. When reservoir gets to full pool level, we actually have 1 meter extra height above the full pool level for flooding or inundating area design. And this is the big model. Earlier slide I explained how we use the soil data, GSRGO data, to create hydrology group, and the land use data to create the land use classes and combine them together using the plus tool. So that way we know like the combination, and the table earlier I showed. So we reclassified that plus raster to provide curve number for each combination. So that way we obtained our runoff raster for the entire watershed that would provide water amount for proposed reservoir. And this is the field time calculation, and check that this is a thorough engineering calculation, and we found out the entire reservoir based on our height, so that we do not inundate high value lands or environmentally positive land uses. So we found out that entire volume can be filled in 111 days. That's 1/3 of a year, and that's really very good. And you check that we use zonal statistics to calculate the total amount of water coming to the reservoir. You see that ArcScene based model development process, how we did it. So we use DEM reclassified to find proposed full pole elevation. Our DEM was created from the LiDAR data, 1 meter LiDAR, and basin area, that initial basin area we kind of created by digitizing, so that we do not inundate unnecessary like land uses. So we overlaid that top of the DEM. Then we converted the DEM to a triangular irregular network. That's the TEAN, which is ArcScene based 3D representation of the DEM. Then elevation raster got converted to polygon, and the volume got calculated from minus tool comparing pool elevation to the TIN or the TEAN raster. So this is a huge model. You can see that initial your area of importance. So we created, making sure that we do not inundate most of the areas, like environmentally friendly land uses. And this process entirely at the end tell that how much volume of water will be there in the proposed reservoir. And this seems, the model seems like a flow process, but it is actually an automated model. So this can be replicated by anybody having a ArcGIS software. And they are the results. This is the initial proposed like surface area. The blue line in the left is our reservoir, and you check that we kind of superimposed it over the property boundaries, and we made sure that we do not inundate high value properties. And at the same time we have the in the background the elevation file DEM is also shown here. And ArcScene based model provided us the decision support not to flood many properties and the side riparian forest. We already saw the modeling flow process. Now this 2015 Georgia Mountain Research Center, actually the LiDAR slope created from 1 meter DEM, that was at the location of the your reservoir. So it was 1110 US feet elevation, like the full pool level elevation. It was relatively flat wetland earlier, and it didn't really flood other side forest or high value lands. A 2018 flood event caused around 188,000 gallons of raw sewage to spill into the creek. Now this reservoir can help this kind of unwanted your environmental quality degradation things to spread to the downstream. And because it would be a reservoir, maybe these total suspended solids or the other impairment can be settling down to the bottom, and that way this will act as a wetland, and wetland as the kidney of the nature. So we know that. So it kind of help decreasing the impact of this kind of swell spill that happened in 2018. And you can see this ArcScene based visual, which was designed as an environmentally friendly small urban reservoir. You can see the blue area, that would be our reservoir inundation area. And this shows the reclassified DEM at 1,110 US feet. That is our pool level plus 1 feet of extra we keep. So that means all these areas will be inundated. And finally, we use the raster to polygon conversion tool to create the reservoir basin area, surface area, and which is shown in a oblique. So thus we were successful in designing this small reservoir using the proper engineering approach. At the same time, we make it environmentally friendly and also friendly towards the urban and your suburban centers. So the summary and conclusion: under normal circumstances, Big Creek averages approximately 40 cubic feet per second of discharge. And you saw that using geospatial technology, we created a model. We exactly calculated cell by cell runoff or discharge amount coming, and using your zonal statistics, we could calculate the total amount of water that is running into the reservoir or the dam location we proposed. We use ArcScene based automated geospatial model that is very unique and also an innovative approach to design the reservoir, emphasizing on not inundating environmentally sensitive land uses and urban or suburban high value lands. And this study should be replicated in most urban and suburban development centers to counter environmentally unfriendly activities due to development of excess impervious land uses by creating easy green spaces in the region that would have multiple economic and socio-cultural advantages. And it to be noted that Atlanta area is very prone to climatic change impact. In 2007 and after that several years, in between until today, we have drought years, and during drought year, your Lake Lanier, which is the drinking water supply source for mostly around 5.5 million people in Atlanta, including your Forsyth area, in the drought period or drought year, the pool level or the reservoir level went drastically down. So water supply gets kind of stressed. So that is the reason this kind of small reservoirs, if built in most of the urban centers or suburban centers with thorough your geospatial analysis, geospatial technology based thorough analysis, then they can, at the time of water need, can be of help. And this type of small reservoirs kind of similar to the rechargeable ponds we are constructing if a new development happens, like a new subdivision got created. So instead of creating very tiny rechargeable pond, these small reservoirs can be built. They would help in not only groundwater recharging, it would help for flood control, it would help for recreational activities. It would also help for any kind of water quality or water impairment stops settling down, like a wetland activities it will do, and also it will enhance the flora and fauna biodiversity surrounding the urban centers, and urban center folks will be helpful. Thank you. And contact is Sudhanshu Panda at UNG.edu.